Hi everybody. In today's lecture we'll discuss norm and trace, which are two important concepts for field extensions. So these are also studied in exercises in Damit and Foot in section 4.2, exercises 17 through 26. On the other hand, they're a little bit too important to be just left for exercises, and I want to spend some more time. While they give you some computational flexibility when you want to prove something, and besides, they're essential in algebraic number theory, so it's worthwhile to discuss. So in the setup that I'll use, so we'll suppose that K over F is a finite extension of fields but not an arbitrary one, such that K is contained in some L containing K, such that L over F is Galois. Now, we'll see soon in the lectures that this is not the case always. I mean, so you need an extra condition. K over F should be a separable extension, and in this case we'll show that L always exists. But okay, for this lecture let's assume this happening. If K over F is not separable, then you will need slightly different definitions than what I'll write down here. Okay, so in this case we define following. Say alpha is an element of the field K. We define the norm of alpha to be simply, I have to be a little bit careful in the notation here. It's norm from K to F, so it's very important to specify which field extension you're talking about. Okay, now from K to F, there's a product of sigma alphas, where this sigma ranges over all embeddings of K okay. All right. So another way to think about it is you can think of all elements in a Galois group L over F, but you just take some different coset representatives for the group corresponding to K. So sigma H distinct cosets where H corresponds to K. Okay. So, what you want to get is exactly the degree of K over F many embeddings of K, and that's how many they are. So you get all possible conjugates. Well, in particular, if the extension K over F is Galois itself, it's a little bit easier to write down maybe. Itself, then you don't have to go all the way up to L. K is equal to L in this case. You can take that. Then this norm is nothing but the product over all automorphisms in the Galois group. Now, I mean, if K over F is Galois, then all embeddings are automorphisms. So, I mean, this is fine. Okay, now some properties of norm. The first and foremost is that norm of alpha is an element of the base field F. And the second thing is norm is multiplicative. So you have this equality. Norm of alpha times beta is equal to norm of alpha times norm of beta. And the third is this relation to the minimal polynomial of alpha. So suppose that let's say m alpha x, which is, let's say, x to the d plus ad minus 1, x to d minus 1 plus all the way to a0 is, well, this is in fx, let me also write that, is the minimal polynomial of alpha over f. And, well, this degree doesn't have to be the degree of the extension. Well, let's also n be degree k over f. Then d divides n. And the norm of alpha is minus 1 to the power n times a0, this constant coefficient in this polynomial, to the power n over d. Well, particularly interesting is when d is equal to n, then this power is 1. Okay, that would be fine, and that would exactly correspond to some simple extension with primitive elements alpha, and in that case this works. But this also takes care of the possibility where that doesn't happen. I mean, you could have a lower degree minimal polynomial than the degree. Okay. Now let's try to sketch the proof of this proposition. First of all, why is this norm in the base field? Now, by the fundamental theorem of Galois theory, well, we know something. Well, maybe K over F might not be Galois, but it's contained in a Galois extension, L over F, by our assumption in the beginning. This is Galois. Right. And the fixed field of the full Galois group, G equals Galois L over F, is the base field. So if you want to show that something belongs to the base field, it's enough to show that it is fixed by every element of G, right? So enough to show that is fixed by every element of G. So let's do that. Okay, so let's give some names to the embeddings. So say sigma 1 up to sigma n are the distinct embeddings of K. I always think about them as members of G at the same time, or coset representatives, whatever. I'll not be very precise on that point. Okay, and say sigma is an arbitrary element of G. Well, actually, the proper way to think about it is, I guess, as coset representatives and G acting on the left on these coset representatives. But never mind. So sigma of this norm would be simply sigma applied to the product and you just get sigma sigma I of alpha. But now the point is, if sigma 1 sigma n is a complete set of distinct embeddings, then if you compose them with sigma on the left, then this is just a permutation of them. This is just a permutation. So the result is again the norm of alpha. The proper way to say this group theoretically would be, I mean, these correspond to different left cosets of H, and if you compose them on the left by sigma, you again get the same list of cosets, one for each. Okay. And this shows that nkf alpha is fixed by all group elements, so it must belong to the base field. So this is the proof of part A of the proposition. Now for part B, it's much simpler. You just use the fact that all the sigmas are field isomorphisms. So let's use the same notation above for the embeddings. So if you have norm of alpha times beta, it should just be this product. But each of these sigma i's is an isomorphism, so you could as well separate these and even the product. And this gives you the result immediately. Okay. Now, let's look at part C, the relation with the minimal polynomial. Now, okay, well, I mean, let me do this assuming that we are working in a splitting field, which doesn't change much in the proof, but okay. say m alpha of x is x minus alpha 1, x minus alpha 2, up to x minus alpha d, by passing to a splitting field if necessary. And alpha is the first of these roots. Okay. Now the whole point, I'll just be sketchy here. Okay, I mean we proved much before that you have an embedding of k taking alpha to any one of these roots, right? Any one of these roots of the minimal polynomial, and you have an equal number of embeddings for each of these roots. So for each I, there exists an embedding of k over f such that alpha is sent to alpha I. Furthermore, for any two distinct roots here, we have an equal number of such embeddings. I'll leave this unproved, but it's easy. But then it's kind of clear because this what is nkf of alpha, it is just the product over all distinct embeddings, but our observation says that each of these has to appear an equal number of times here, so there's no chance, but this must be equal to alpha 1 up to alpha d to the power n over d. But then if you compare this with the constant coefficient of the polynomial, you immediately get the result. Okay. Now this pretty much wraps up everything I want to initially say about norm. Now there's a closely connected concept of trace which we'll define. I'll write the similar properties but leave the proof as exercise. So same assumptions. For k over f above, so it's contained in some Galois extension L over f and it's finite. Okay, so we'll define trace. Okay, let alpha be in k, define the trace of alpha to be, again I have to specify from where to where I'm going, from k to f of alpha is, again this time instead of product you could use sum sigma of alpha, where again sigma goes over, I mean it ranges over all distinct embeddings of k. Okay. Now we have an analogous proposition for the properties of trace. The first part is the same. Trace of alpha must belong to the base field. Then, okay. Norm was multiplicative, trace is additive. And the third is its connection to minimal polynomial. So if again m alpha x equals x to the d plus so forth. Okay, let me be careful here. ad minus 1 x to the d minus 1 plus so forth a0 is the minimal polynomial of alpha, over f, then you can compute the trace to be simply minus n over d a sub d minus 1. We decided that d must divide n, and yeah, it's minus n over d times the coefficient of x to the power d minus 1. Okay, the proof is entirely similar, so let me just skip the proof and leave it as an exercise for you. Well, one comment, I mean, you must have realized the similarity and also in the naming, while trace is like trace of a matrix and norm is very much like a determinant. Actually, the definition could have been made by using matrices, but then, okay, if you do it like that, you have to prove some independence of basis or something like that. And actually, that's a good idea if you don't have a separable extension also. I mean, that definition is a little bit more general, but let me stick to this one here. Okay. Now, let's do some examples. Maybe the first thing that we should do is a quadratic extension of Q, right? Or, okay. Okay, maybe more generally, let's f be in a field whose characteristic is not 2, okay, and the non-square in F, and K is simply F adjoint root T, a typical quadratic extension. Okay, then we know, of course, that K over F is Galois. Okay, with Galois group, okay, let's say G is the Galois group. Then its elements are, we know very well, it has got two elements, the identity element and tau, where tau of A plus B root T is A minus B root T, right? Okay, so what is trace and norm in this particular case? They'll give some familiar stuff. Norm of A plus B root T should be, okay, product over all embeddings of K, but in this case, embeddings are automorphisms, and you have A plus B root T times A minus B root T, and if you multiply them, of course, you get A squared minus B squared D. I mean, think of the example D is equal to minus 1, so that over F equals Q, so that would give A squared plus B squared, which is modulus squared of a complex number, so it is a very familiar quantity. Oops. Okay, let's also compute trace. Okay, this time you simply add them and you get 2A. Okay, so that's a perfect example where we know that it is useful, right? This, we saw these quite a bit of times in different settings. Okay, now let's do some cubic example and show that how these can be used for making some computations easy. Okay, so the problem is show that cube root of 3 does not belong to Q adjoint cube root of 2. Actually, I mean, this precisely came up in one bonus question in our exam, but at that time, I mean, one had to do this quite explicitly and it was a little bit ugly. Now, with the use of trace, this can be made quite quickly. Suppose for a moment, let's do a contradiction. Suppose cube root 3 belongs to this field. Okay, then you must have such an equation. Right, 1 cube root 2 and cube root 4 is a basis for this field over Q, so you would have to have such an equation. Now, the pedestrian way would be to cube both sides and try to get out of these equations, which you can do because, you know, there are some symmetric functions and you can play with them. However, now let's take traces. Okay, take traces of both sides. So how do you know the traces? I mean, here we use a connection to minimal polynomials. Now the minimal polynomial of cube root 2 over Q is, as we know well, x cubed minus 2, right? And what do we have to look for? Trace, I mean, trace is the subleading coefficient, so it's going to be the coefficient of x squared, but that's 0. So trace of cube root 2 must be 0 just by looking at the minimal polynomial in this case. Likewise, minimal polynomial of cube root 4 is x cubed minus 4 because that's irreducible and cube root 2 satisfies it. So this element also has trace 0, and finally minimal polynomial of cube root 3 is x cubed minus 3, and consequently that also has trace 0. Okay. Now apply trace to both sides of this equation and let's write what we have. We have trace of cube root 3, so just from star, let's say, by star, 0 must be equal to, okay, now here maybe we have to be a tad careful. Trace of A, so you have to know trace of 1. Trace of 1 is not 1, it is equal to the degree of the extension times 1, so it is 3. Just look up the formula. 3 times A, of course, but the other two give 0 and 0. Anyway, the conclusion is A is equal to 0. Okay, so you simplified your relation a little bit. So let's continue. Now you could play the same game, but now maybe after multiplying both sides by something like cube root 2. Okay, what does that give you? You'll have cube root 6 here equals b cube root 4 plus, okay, cube root 8, but that's 2, so you get a rational number, so 2c. Now, play the same game, take traces. Okay. Trace of cube root 6 by a similar argument, because its minimal polynomial is x cubed minus 6. This is 0. Trace of cube root 4 is 0. Trace of 2c, well, trace of 1 was 3, so this is going to give you 6c. But anyway, this gives you that c must be 0. So we are going towards a contradiction. If you go back to star, that's going to give you cube root 3 equals b cube root 2. But I mean, you can see, I'm by trace or otherwise, maybe easier is 3 over 2 equals b cubed, where b is rational, and that's definitely a contradiction. So this shows that, I mean, with use of traces, you are kind of linearizing the problem, and you don't have to deal with complicated cubic equations to make this deduction. Okay, let's do something else. Okay, now I want to solve a couple of exercises from Damit and Food. So let me write the numbers here. 14.2 exercise 21. Okay, so it show that if k over f is a Galois extension, then there exists alpha in k such that its trace is not 0. Okay, seems like a generic condition, but how to really prove it? Okay. Well, by definition, this trace of alpha would be the sum sigma 1 up to sigma n alpha, where these sigma i's are the distinct embeddings of k, k into L, say this Galois extension that we talked about. So I'm using the same notation that we started in the beginning. Okay. In particular, well, these sigma 1 through sigma n are L-valued characters. Of k. This is something we talked about when we were proving the fundamental theorem for Galois correspondence. And the key thing is that distinct characters are linearly independent. So, and they are linearly independent over L, this even big field. So, but if you have all these traces to be 0, then what does this mean? This means that as a function, the sum of all these characters is equal to, well, the sum of characters is a function, it's no more a character. But anyway, this is going to be the zero function, but this contradicts the linear independence. And this is a contradiction, so hence you must have something with non-zero trace. Okay, so that's a proof. Now, let me move on with the next exercise again in Damitan food, because that's kind of heading somewhere. Again, this is 14.2 exercise number 22. Okay, again the assumption is, okay, this time you want K over F is Galois. Oh, okay, in the previous exercise, I'm sorry, I assumed that K over F is Galois, so in the previous exercise you could take K equals L, you don't need this big L, but anyway, it's still true. Okay. Let sigma be an element of the Galois group. K over F. Okay, and part A is if an element of K is of the form beta over sigma beta for some non-zero beta in K, then it must have norm 1. And similar thing for trace. If alpha is of the form beta minus sigma beta for some beta in K, then it must have trace 0. Okay, so this kind of special elements having norm 1 or trace 0, we'll see why this exercise is kind of significant for something. But anyway, to prove these is not really difficult if you just write down the definition. Let's do it. Okay, so how do you go for A? Well, this norm of alpha, well, norm is multiplicative, so I could do this, right? The denominator is not going to be 0 because beta is not 0. So if you use previous notation, it is just going to be a product over sigma I betas, and down here you'll have product of sigma I sigma betas. But then again, it's the usual story. The sigma i's composed on the left or right will again give you distinct representatives. So this is going to give you 1. Okay. Now for B, it's kind of similar. If well, we are looking at trace, and trace is additive, therefore this is going to be trace k over f of beta minus trace k over f of sigma beta. But then trace can be written down as a sum sigma I sigma beta. Again, you'll get a permutation of them. Maybe I should emphasize that now our extension is Galois, so the sigmas go through all automorphisms, and therefore sigma sigma i's composed on the left or right again is going to run over the same automorphisms. You don't need left cosets here because the extension is already Galois. Okay, but again this is going to give 0. Fine. Now this this was fun and not too hard, but actually this was kind of a preparation for some very nice theorem. This is due to Hilbert, I suppose. Okay. Now this gives kind of a converse of the previous exercise in a specific case. If the extension has cyclic Galois group. So say K over F is Galois extension with cyclic Galois group of order n, generated by sigma. So the group is Z over NZ and sigma is a generator. And suppose that alpha in K has norm 1. Okay. Then there exists some beta in K such that alpha is beta over sigma beta. So this is kind of a converse. I mean, we know that all these elements have norm 1, but this is saying that's the whole story. I mean, so any element of norm 1 can be written in this form for some beta. Maybe I should also comment, there's also an additive version with trace and the condition trace equals 0. Okay, you can easily figure out what it should be like. Okay, let's prove this now. Okay, now let's write down the norm of alpha explicitly. Well, the point is we know all elements of the Galois group and they are, given by powers of sigma. So the first element is identity in the group, and then you have sigma, then you have sigma squared, so forth. And we also know where to stop. The order of this element is n, so this last thing we'll write here is sigma to the n minus 1 alpha. This is assumed to be 1, right? Maybe notable is, in particular, all of these things are non-zero, so their product is 1. Okay. Now we want to cook up this beta explicitly. So okay, here's how it's gonna go. Well, the first comment is these 1 sigma, sigma square up to sigma to the n minus 1. These are k-valued characters on k. And they're different, so they're k or distinct, maybe, let me say. So they're linearly independent by this general result. Right, that's this key fact coming up again and again. Okay, now in particular, the following thing cannot be 0. Okay, we'll use this in a very specific way. I'm writing a very specific linear combination of these characters now. Each time we're introducing one more piece to the coefficient. So the next one is going to be alpha times, sigma alpha times sigma square alpha. Well, all this is a coefficient, but now I'll use sigma cube. Just go on until the end. So the last coefficient that I'll write will be kind of huge. So alpha, sigma alpha, go all the way to sigma to the n minus 2 alpha. Well, that's just the coefficient, and the character is sigma to the n minus 1. Well, however ugly this looks, this is just a linear combination of these characters, and since they are linearly independent, it cannot be 0. Okay, so this implies there exists, this is a function, right? So there exists theta in k such that the value of this function on theta is not 0, right? So just write that down, and that's going to be beta. Let me not write the whole thing, but just the last one maybe. Okay, so this is gonna be the element that we'll try to catch. Okay, now the point is, if you apply sigma to beta itself, and if you carefully look at it, you just get 1 over alpha times beta. Let's try to see some signs for that. So the first thing that you'll get is sigma theta, of course, which is 1 over alpha times the second thing here. Plus, the next thing that you're going to get is sigma alpha times sigma square theta, which is again 1 over alpha times the next term. I didn't write the next term here, but it's written up here. You don't have the alpha, but you have the sigma alpha, and you have sigma square theta for sure. So it's again 1 over alpha times what you had. Now, of course, the surprise comes at the last term. But here exactly we're going to use that. The group is cyclic. So this is going to give you what? Sigma alpha, sigma square alpha, all the way to sigma to the n minus 1 alpha times sigma to the n theta. Now there are two things to observe. The first is this is just theta, because sigma to the power n is the identity. And the second thing is the norm of alpha is equal to 1. That was the big assumption. So, and this is everything except alpha in the factors of the norm. So this is equal to 1 over alpha. It's again 1 over alpha times the first term here, so it sort of wraps up to the beginning. But overall, the conclusion is this is 1 over alpha times beta, and that gives us what we want. Alpha equals beta over sigma beta. Okay, that's cool. Okay. Now, as a final thing, let's use this in an example. Okay, this is again an exercise in Demet and Foot, but it is of historical importance even. So prove that all rational solutions A, B, and Q of this Pythagorean type equation, a squared plus b squared equals 1. This is like a Diophantine equation, right? So two rational numbers whose square add up to 1. These must be of the form a equals s squared minus t squared over s squared plus t squared, and b equals 2st over s squared plus t squared for some st in Q. Okay, this is kind of a classical thing, and there are kind of maybe tens of ways of seeing that. I mean, some geometric, some more number theoretic, and so forth. But here, let's use Hilbert's theorem 90. And if you use that, it is very, very short. So now all you have to observe is that Q adjoint I over Q, well, this is a quadratic extension, so it is Galois, right? Galois extension with, of course, Galois group is also extremely simple. It's just two-element group. Let's say 1 sigma, where, of course, sigma is the good old friend, complex conjugation, right? Okay. Now, a squared plus b squared is, of course, a plus ib times a minus ib. So it is nothing but the norm of a plus ib, right? So a squared plus b squared equals 1. This Diophantine equation holds if and only if the element a plus ib has norm 1. And this is just the right setting for Hilbert's theorem 90. So if a squared plus b squared equals 1, by Hilbert's theorem 90, there must exist some beta, which we'll call S plus IT in Qi, such that, you know, alpha equals A plus IB is equal to beta over sigma beta. But just write down what this equality says and unwind it, and you'll get what you want. So A plus IB equals S plus IT over S minus IT. But then, you know, multiply with the conjugate once again. This is going to give you S squared plus T squared down here if you multiply and divide by S plus IT. And if you carry out this is going to give you exactly X squared minus T squared over S squared plus T squared plus I times 2ST over S squared plus T squared. Now you equate the real and imaginary parts, which gives you the result. Okay, so this is a very nice application, and there are many more. Okay, so in this lecture we talked about norm and trace. The story is far from complete. This is quite an interesting topic, and there's much more to be said. But this is all for today. Thank you.